Good morning, and thank you for having me here this morning. So, ironically, the only reason why I came back to Amsterdam back in 2017 is because I changed jobs. I left NASA and I started working for a Hyperloop technology company. And my very first business trip was actually to come to Amsterdam because you also have a local technology company here. My background is all engineering. Aerospace engineering is all my degrees. I worked for NASA for about 16 years, and then I left for the private sector, specifically to work on the development of new transportation systems. And I decided to do that for a whole variety of reasons. The primary one was because I felt like one of the things I didn't have in my career was any kind of business background, business development, sort of customer engagement with people other than very nerdy scientists that I work with at NASA. And so it was time for me to do something else and put my engineering skills to the test. But what I will say is that the space program is a very unique environment where all you do is handle very complicated problems. And the challenge with the space program is that you basically can't use an agile methodology in the traditional sense, because when you finally do launch your product, it's pretty much the first time that you're doing it, and it has to work the first time. So it's slightly different in that sense, but in terms of the engineering skills that go into making something really complicated come together, you can take those lessons learned with you to wherever you go in your career. And so I worked on the development of propulsion systems for about 5 years for deep space application with the Dawn mission. By a show of hands, has anyone heard of the Dawn mission? It's not as familiar, but it's a spacecraft that went to the main asteroid belt to visit 2 different protoplanets, and you had to have a very special propulsion system to get there because it's very far away, and that was my PhD thesis topic. Then I shifted over to work on Mars entry, descent, and landing systems. Thank you for the intro on that. And then Venus entry, descent, and landing systems, and then Earth re-entry systems. And then I did something from the space station for about 5 years, which ironically has a follow into quantum computing. So I hope to meet up with the press center over lunch today. And that's something called the Cold Atom Laboratory. And then I left to join the private sector to be an executive at a Hyperloop technology company. And then I did that for about 1.5 years, and I left that to start my own company, which is an urban air taxi company. And so I think during the course of my career, I have wanted to work on very challenging things because I find it to be very stimulating and intellectually challenging, and you just get to solve really cool new problems. But I think the one thing that bothered me was that I wasn't really doing anything to help people here at home. And I think we all know that one of the biggest challenges that we have as a species, as a planet, is climate change. And there's a good analog to that by looking at the neighboring planets. So obviously the planet in the middle is Earth, our home. The planet on the left-hand side is Venus, which is one planet in from us. And the planet on the right is Mars, which is one planet out from us. At the formation of our solar system, all of these planets were actually far more similar to each other than they are today, which means that over the course of the past 4.5 billion years or so, these planets have evolved at a planetary level with different types of climate change phenomena. Venus, which is the one planet in, has a surface temperature of 475 degrees centigrade and a surface pressure 100 times the surface pressure on Earth. And then Mars, one planet out, has a surface pressure 1% of Earth and a surface temperature which is quite cold. So we really can see by looking at our neighboring terrestrial planets that indeed climate change is a planetary phenomena. And of course, both of the other 2 planets closest to us we cannot inhabit in the traditional sense, because you don't have water on the surface and you don't have a thick enough atmosphere nor an oxygen-based atmosphere to be able to survive. So we can really see that climate change is something that we do need to deal with here at home, and I know Europe does a much better job on that front in terms of shifting over to renewables. In the country where I live, Los Angeles-based California in the United States, obviously we're doing more in our state, but across the country we're not doing enough to address it, and so that's something which is a challenge for us as a people. But my training has always been in engineering. Show of hands, who is computer scientists, engineers in the room? I guess probably like 80, 90%, which is not to be expected. So I'm a big fan of engineering, because engineering obviously is applied science, using math and science to develop new technologies. And one of my favorite quotes actually is from the father of modern aerodynamics, which is that basically scientists observe the world as it is, and engineers create the world that will be, using the tools of math and science to create new technologies. And I think one of the best examples of that, of course, is flight, aerodynamic flight, wing-borne flight. But what is kind of interesting is that there is another very famous scientist, Lord Kelvin, a British scientist who invented the Kelvin scale, right? So huge thermodynamic applications there due to his work. But he actually said in the late 1800s that basically wing-borne flight, lifting body flight was not possible. And then only a few years later, the Wright brothers obviously proved him wrong, having flight going in the Midwest of the United States. And today, of course, we use aircraft to get around everywhere. So it is interesting that when you do something which is really complicated, complicating. When you do something which is sort of like changing the way you think or thinking outside of the box, oftentimes you'll find people who'll say that it's not possible. And our jobs as engineers and computer scientists is to prove them wrong by creating these new solutions that hopefully can make the world a better place. And a more modern quote on that front is from the movie The Martian, or the book The Martian. By a show of hands, how many of you have seen that? Still a high percentage, right? So basically in the face of overwhelming odds, you're left with one option, which is to science the shit out of it, or engineer the shit out of it, I think is more appropriate in that case. And it really does lead to the topic of the talk today, which is that we can make this science fiction world that we see, hopefully it's a utopian science fiction world, not a dystopian one, a reality using the tools of technology. And one of my favorite quotes is in the Science Fiction Museum in Seattle. I don't remember who it comes from, but people who like science fiction are filled with a sense of wonder. And you take that sense of wonder and then you translate that to new technologies. And so one place where new technology is really important, of course, is in the mobility sector. And you can take a historical look back through time. So back 3000 BC is when we believe the wheel was invented. And so you can imagine how having the wheel attached to a cart really enabled or transformed human society in terms of moving around goods and services, facilitating people's lives so they could live more comfortably. Move forward a couple of thousand years, the Industrial Revolution was enabled by the development of basically the train. Right? And so the train allowed you to, once again, move goods and services at fast speeds over long distances, and human society grew as a result, and economies grew as a result. Move forward a couple of decades, internal combustion engine, the development of the individual car, personal mobility, also transformed human society. One could make an argument, perhaps in not the best way, as a result of the congestion which has come about on ground-based roadways today, such as highways and freeways, especially where I live in Southern California. But nevertheless, it did change the way that we lived. So not everybody lived in urban centers. People then started to live in the suburbs and further out, even into rural locations, using cars to go back and forth. Move forward a couple of decades later, and the development of aircraft, which enabled essentially a connected society, global commerce, and all of this because of the development of these transportation technologies. So you can really see from a historical context that transportation has transformed our society, and in a way that has grown our economies, and probably what we all do today is because of that, if you take a look back at history. But of course, it does come with its challenges. One of the primary ones, of course, is congestion on the road, which leads to congestion on the air, the use of internal combustion engines, whether it is for jet engines or whether it's for cars, also has this carbon footprint associated with CO2 emissions. So we have that huge environmental challenge, which comes from transportation technologies. And then from a more sort of geopolitical sense, there are, when goods can't be transported properly, they sit on the ports, they sit at airports, they sit on the roads, and therefore it actually takes a hit on commerce. So there's money lost. The good news is that when you can say money is lost, all of a sudden you have a business case, right? So all of a sudden you can start a company which is going to solve a transportation problem with new technology, greener at the same time, and also you'll be able to get investment money because you have a business case for it, which I think is important in order to be able to do a lot of things that we do as entrepreneurs in this room. But one of the challenges, of course, though, is that mass transportation has largely been sort of the domain of companies which have existed for decades or hundreds of years, also in the domains of the governments. And sometimes you don't get the same level of innovation which required. So you kind of have to have a sort of a disruptive mindset to coming up with new transportation solutions, as opposed to doing more of the same. And so one of the ways to do that is to think about it in a systems engineering sense. I spent many of my years as a systems engineer at NASA, which is basically figuring out what the customer wants and converting it into engineering requirements all the way down to the component level as necessary. So from a transportation system perspective, we think about what the customer wants. We want to reduce travel time. So that's pretty obvious. You want to go faster. Passenger experience. Nowadays, everybody wants to have a good experience, whether it's the way they feel, the way they interact with it, and of course, the environmental impact. Another one is capacity. How many people do you need to move around per hour, per direction between point A and point B, or point A and point C? That's actually very easy to quantify nowadays because of all the data that's come out from even the survey you just did, for example. Safety is an important one. I think we've all heard in the news issues with the Boeing 737 MAX. Any new form of transportation has to inherently be safer than its predecessors. Otherwise, it just wouldn't make sense, and that's not good engineering if it's not safer. Cost is also key. So transportation and mobility is largely about public acceptance and public accessibility. If the transportation cost is too high, the public doesn't have access to it, and therefore it can't be used. And so it's really important that whenever we come up with a new transportation system solution, it's something which can be implemented all over the world and can also be affordable. And that really comes down to an actual engineering constraint, because you have to design something which is affordable. And of course, the most important one is environmental impact. And so all new technology solutions nowadays, especially in this space, should focus on that environmental impact. So how does one innovate? So this is where I think we all come in, which is that doing things differently, disrupting, actually requires an entrepreneurial mindset, and this is where startups could be quite successful, and they have been quite successful. And even in my 2-year journey so far in the private sector in this transportation startup space, and I use, of course, images from, I guess, what would you call popular culture in the United States in terms of the startup environment, but I think this is very much true. It was true for when I worked for a Hyperloop technology company. It's true for the Hyperloop technology company that exists here in the Netherlands, which is HART, and it's true for my new company, which is Urban Air Mobility. So when you have a disconnection from the way things are traditionally done, all of a sudden you can see different solutions to the same problem, and you'll be able to innovate in a more interesting way, which then comes to the first new interesting mode of transportation, the Hyperloop. So when people think about the Hyperloop, this is what comes to mind first. Almost everybody in the United States thinks Elon Musk invented the Hyperloop. And the reality is that the Hyperloop did come from the domain of science fiction. So if you take a look at science fiction from the 1960s and 1970s, the Jetsons, for example, you saw people traveling in tubes. So once again, science fiction providing that sort of like initial innovation kickstart for the rest of us out there who like the science fiction. And in the case of California, and in the case of Elon Musk, the white paper that was written in response to a high-speed rail project which was being kickstarted in the mid-2000s in California. And so his argument was that, why do high-speed rail? It's old technology. Why not do something new, something more efficient like a Hyperloop? And that's kind of what brought it to the forefront. But it really does have its origins in science fiction that you can see in these examples here. And so the Hyperloop is a great idea. I'm a huge supporter of it. I hope it happens in the next 5 to 10 years or so, and it probably will somewhere in the world. And to describe what the Hyperloop is, it is actually a combination of things that already exist. So the primary principle of operation is that you have a maglev train, magnetically levitating, electrically propelled, traveling through a vacuum tube. A vacuum tube basically means you're sucking out all the air. When you suck out all the air, you essentially cut down aerodynamic drag to almost zero, or for all intents and purposes, from an energy consumption perspective, it's zero. And if you want to go faster and faster, drag actually goes with your speed squared. So if you can get rid of that drag force, you can actually become very, very efficient at high speeds compared to any other mode of transportation. Because it's ground-based transportation, it can operate off of the grid, and if your country's grid comes from renewables like wind and solar, then all of a sudden you can have a transportation solution which is fast, high speed, and environmentally friendly. This tube that you see here, you can have solar panels on the outside, which means you can even generate your own energy for this fast-based transportation over long distances on land masses. So it's a really great transportation system solution, and as a result, the people who took this up were different startups from around the world. The one I worked at was based in Los Angeles. We had a test facility where we built a half-kilometer Hyperloop that you can see me standing in front of in the desert just outside of Las Vegas. If you Google that on Google Maps, you can actually see it. It's like a long tube. And so we used that to demonstrate the technology. So we did use an agile methodology in the sense that we built a 70% scale prototype of the vacuum tube and a vehicle to travel inside of it to demonstrate basically the vacuum operation and the maglev aspect of the passenger vehicle. There is a test track being built in Toulouse. I think there's probably 2 of them being built in France now. There's a company in Canada, another company in the United States, and then I think you also have a test track being built here in the Netherlands with HART, which is the other local company. So all of the companies working in this space are startups. None of them are traditional transportation companies. They're partnering with traditional infrastructure companies, for example, because a lot of this is related to infrastructure such as laying roads and bridges and sort of right away, but nevertheless, all in that startup space because it's a very disruptive way of doing things. But ultimately, to drive down the cost, you have to come up with other solutions. And so here, we can actually take a look at the coupling to the software community, the software industry, where that if we can address where are the places in the world that have the ridership that can make use of a system like this from going to point A to point C, And how do we make it on demand? And that's where you can use the data that exists of people's current transit patterns, optimize it to figure out where's the right place to implement one of these systems, because you have enough ridership and therefore you can get the cost down when you utilize it. The other element of driving down the cost in the case of the Hyperloop is to make the system autonomous. And the reason for that is with autonomy, you can get an optimization in terms of capacity of pushing people back and forth, and then you have reduced operational costs because you don't have to have someone driving a vehicle. And at the speeds at which a Hyperloop can go, which is in excess of airline speeds, you can't have a person with reaction time operating that system. So you may have an operator in the loop, but they would be there for safety purposes, but the driving has to be done autonomously. The good news is that the automotive sector is already working on autonomous driving vehicles for use in dense urban environments, which happens to be the most challenging problem in autonomy. And the reality is that you can take a lot of that work, leverage it, and put it into something like a Hyperloop system, which is a very controlled environment as you're inside of a vacuum tube. And so therefore, you can have a lot of your technology development and the capital expenditure associated with that conducted by people like Google at Waymo, for example, right? So you can see how these systems can couple to other modes of transportation, which then brings me to the next topic of my talk, which is urban air mobility. So I worked for a Hyperloop company for a year and a half. It was really fun and exciting, and I enjoyed it. But as I expanded my network of people in the space by attending conferences like this one, I've been to many GOTO conferences, I met other people in the space, and I met a gentleman who asked me to start up a company with him, which is an urban air mobility company. And I give you an example, once again, from science fiction, the Jetsons, flying cars. Everybody knows that terminology. It's a misnomer. It's not really the right term, because there are aircraft, they're not cars, and they're not going to drive around the road, because it's a very different use case and a very different engineering design. But nevertheless, the company is used, the country or the world is used to that term, so this is the space, but it largely is an aircraft which has the ability to take off and land vertically. And so for those of you who have ever been to Los Angeles, in the room, people who've been to San Francisco, Mumbai, Bangalore, Delhi, Kolkata, these are cities who have a congestion like nothing else. Like Amsterdam is really nice from a traffic congestion perspective. It's not as bad as many places in the world. So if you live in urban environments and you want to be able to get around to suburban locations or rural locations, if you wanted to do that much faster than driving, and a subway doesn't exist yet because either you can't afford one or it can't be built, you can look at another way of this, which is basically taking to the sky. And therefore, you get rid of the congestion on the ground problem because you're operating in the dimensions of airspace, which is 3D. So I'll show you a video of what an implementation of that might look like. So that is the video of our concept vehicle that we call Mobi-1. My company is called Aerospace Experience Technologies, and it's based in Detroit, which is in the Midwest of the United States, and it's the automotive capital of the United States. And some people call it the automotive capital of the world, because that's kind of where it started, but of course, there's many car companies that exist all around the world. So the solution here that is shown in that video is an electric vertical takeoff and landing aircraft. Our design is a tilt-wing aircraft, which means that it can take off and land vertically with the wings shown in the position here, or it can take off and land like a regular airplane using existing runways at either general aviation airports or at commercial hubs. And so by having the ability to take off and land vertically, you can therefore land in dense urban centers, and you can use existing infrastructure such as rooftops, which are already set up for this, new vertiport locations that might be created in the future, or even parking lots, which exist all around cities, at least in the United States. Now, something that people don't realize if they don't work in the transportation space, and if they're not a pilot, like I'm a pilot as well, I fly for fun, I'm a general aviation pilot, which means people can't hire me to fly for them, but I can fly my friends around and things like that, is that there are airports all over the United States called general aviation airports, which are used by people like me to fly for fun, but they're not used by most people to fly. And so when you look at the cost of infrastructure, it turns out that ground-based infrastructure is the highest cost. So if you can make use of an existing infrastructure asset, which is an existing airport, which the government is already funding and is paying people to operate it and the airspace around it, you'd be crazy not to. So one of the arguments for urban air mobility is to make use of that existing infrastructure because it's already underutilized, especially in the United States. Not so much in countries like India. They don't have as dense of a general aviation airport network, but they do exist, and you could actually use instead parking lots and vertical takeoff and landing locations. So this urban air mobility use case is not intended to be long-range aircraft application. It's intended to be short-range application. And the reason for that is that we want to make the vehicle electric. So the only way that we're going to kickstart a sustainable aviation industry by making it all electric is if we can find use cases where you can have an aircraft which operates just on batteries. So range is an issue for electric vehicles as it would be for an electric air vehicle. So the urban use case, which you don't really need more than 100 miles of range on one of these vehicles, enables you to have a fully electric aircraft which can be charged using the grid power which can come from renewables. So this is the way you can kickstart sort of a low carbon footprint aviation solution. Now, over time, as hydrogen fuel cells are developed, for example, you can imagine these aircraft doing regional flights, and over time, if this industry really does take off, pun intended, there'll be more batteries that come out which are better suited for aviation use, higher energy density, and you can get to longer and longer ranges. So that's really the argument behind this and that urban use case. And as a pilot, and it's my hobby, it's kind of a shame, of course, to have an application that I do for fun, which has a carbon footprint. So I would love to have an electric airplane so I could have a lower carbon footprint. So as I showed you with the Hyperloop scenario, prototyping and testing as quickly as possible is the way to go. And so here is an example of one of our subscale aircraft flying in at Detroit City Airport, where we're based. So starting with subscale vehicle development is a way that you can handle or learn about all the different aerodynamic and dynamic stabilities that you need to have for control of the vehicle in a much lower cost mechanism. So the vehicle I showed you there is 1/5 scale, 20% of full scale, and we've built a 1/3 scale to do the same demonstrations, vertical takeoff, transitional flight, and our next stage is to build a full scale aircraft. And so there are other players in this field. There's actually several in Europe. We're doing a different technology solution, which you can see is the tilt wing. But ultimately, if you want to know what the passenger experience would be like, we have this video that we can show you. So one thing that people like to ask me about this is this going to be a self-flying airplane? And so we are designing these aircraft to be autonomous, the ability to fly by themselves, but there would still be a pilot in the loop. There are several reasons for that. One, obviously the regulatory space doesn't allow for not having a pilot in the loop. And two, it makes sense to keep people as safe as possible, and only when you felt completely comfortable that you wouldn't need a pilot and the public felt completely comfortable with that, would that ever go away. But largely, when you fly commercially, when you fly above 18,000 feet, when you fly IFR, most aircraft do have autopilot, and autopilot is utilized for most of the phases of flight with the exception of takeoff and the final approach. So that's already done in terms of having the software control in the vehicle, but of course you still would have a pilot in the loop. So that's just something to give you comfort on that level. Now the other issue, of course, you're probably all thinking is that, well, helicopters are quite noisy. This is not a helicopter, this is not a rotorcraft, it's an aircraft, but having electric motors and having a more efficient system that we have here actually allows you to have significantly lower noise levels. So this would be 2 orders of magnitude less noisy than a helicopter, for example. So more like a general aviation airport. Now, I mentioned before about how do you lower the cost. So any pilots in the room, people fly for fun? Not so many. One. And so aircraft are notoriously expensive. The reason for that is the production volumes for aircraft are incredibly low. Even for general aviation aircraft, they're only pushing out, maybe at most a couple of hundred per year. So cars, on the other hand, they're pushing out, I don't know how many cars come out on an assembly line per day, but it's quite a lot. And so you get economies of scale with mass production, both in terms of the techniques that are used to design and fabricate the vehicles, as well as simply having many units allows you to lower the cost per unit. So if the urban air mobility space does take off, you can actually lower the cost of the vehicle significantly to get it well below $1 million. And because it's actually electric, lowers the cost of operating one of these vehicles. So this actually helps the whole aviation sector in general if you shift over to this electric vehicle, because engine overhaul is the primary cost in maintaining an aircraft. And then something which I think is really interesting and something that we're thinking about, and I encourage other people in the room to think about, is modifications and updates to air traffic control, which largely also have the human beings in the loop. If you could use something like the V2X connected car network to be able to do traffic management and collision avoidance, because the aircraft are talking to each other, their positional space, in time, in altitude, and in all 3 dimensions basically, you can monitor traffic and manage traffic in that way. And that's something that I think people are open to updates in that area, which is very much a software solution. Which then comes to where everything is headed here is that many companies are starting to look as mobility as an end-to-end service, using public transportation, getting scooters, getting rideshare, and then even potentially getting aircraft. So that's where this all couples very nicely to the software space, because all of those solutions, to make it on demand, require that integration. And so whether we're talking about hyperloops, electric cars, or electric aircraft, whatever we can do to stop using internal combustion engines and jet engines and shift over to electric vehicles does allow you to connect the planet in a sustainable way from that perspective. So now, just to do an abrupt change, where are we headed next? We're actually headed next to space. So it maybe doesn't have as much coverage in the news here as it does in the United States, or perhaps it does. I don't spend enough time watching TV here or there. But there are many companies which are working on this in the private sector. So here are 2 examples. On the left, of course, is Blue Origin, which is one of the companies of Jeff Bezos, CEO, founder of Amazon. The one on the right is Virgin Galactic, which is from Richard Branson. And these vehicles are both intended to give you access to suborbital travel, primarily for the purposes of tourism right now, right? So you get to see the arc of the planet from space. You get to call yourself a commercial astronaut. And there are use cases where you can think about using this as traveling over distances for really short speeds, but largely their business case is based off of sort of a tourism aspect for people who are interested. Not cheap, of course, so that doesn't couple to my prior slide about making it affordable. And then there are also companies working on the next thing, which is sending people to low Earth orbit and beyond, space travel. So the picture on the right is from SpaceX, which of course is Elon Musk's company. This is the Dragon capsule, which is already going back and forth to the International Space Station. They want to make a red Dragon version of this to be able to send people to the moon and to Mars. And the image on the left here is me in front of the Orion capsule. So this is a NASA-funded program to send people beyond low Earth orbit, basically lunar applications, asteroid retrieval mission applications, and then of course sending people to Mars. And even though it's a government-funded program, the vehicle itself is designed, developed, fabricated, and built in private industry. So that has always existed in the space program side of things. So you can see that this sector is very interesting, and there's a lot of people in this space, and there's also a lot of venture capital going into this space. So it's definitely a market to be considering in terms of your own companies that you may be working on. So where are we headed to next after we develop these vehicles? It'll probably take us, 10 to 15 years more in the testing space to get to the level that we feel comfortable with using them. But ultimately, what I want to do, is to send people to Mars. I'm not as interested in the moon. You can ask me questions about that if you want to later or this evening. But I would like for us to go to Mars. The reason for that is not sort of a tourism journey, but like setting up colonies there, because if you're going to go anywhere in our solar system, Mars happens to be one of the most hospitable places. It isn't really, but compared to the other ones, it is, in the sense that Mars does have a thin atmosphere, which you can utilize to sort of pressurize your habitats with CO2 and grow plants in that CO2 to create oxygen. And then Mars also has, 1/3 the gravity, so it's a little bit easier on our bodies than floating around in 0 G, for example, or even the 1/8 G of the moon. And the radiation environment is somewhat attenuated by that atmosphere, and you can sort of put yourself under the ground to protect you. So we have been to Mars several times, as was the introduction. This is the program that I worked on, which is the Curiosity rover. So the robotic space program is the precursor of the technology development, which then feeds forward to human exploration of Mars. And so we've got another rover which is launching in 2020 in Europe, as well as with ESA, as well as in 2020 with the human space program. I had dinner with some of my ESA friends last night. They were giving me the latest and greatest on what's going on there. And some of the other really important technologies to enable the exploration of space do come from sort of a much larger set of technologies, not just for space application. One, of course, is artificial intelligence. All of these environments are very challenging on the human body, so wherever you can use robots to do work for people, either as partners or before you actually get there, it makes a lot of sense. And so NASA does spend a lot of time developing robots to do different tasks. Let's say for the space station, the example Robonaut actually was operated in the space station. It can work in and operate in a vacuum environment. And here's one which is a more mobile solution for work on the surface of Mars. And so all of these technologies can be developed in other spaces for other applications, but can also be used for the space program. So it's nice to see these kind of synergies going on between those two areas. So what I do think is interesting, and it does tie in nicely with sustainability, is that in order for human beings to be able to survive on Mars, we really have to learn to be sustainable here at home first. Otherwise, there's no way that we'll survive going out to another planet. And there's the ways that you would do it on Mars is to generate your own power. If you're not limited to a small robotic platform like the Curiosity rover, and you can actually set up a colony, you can set up large areas where you have solar panels, for example, right? So you can take use of the solar energy coming from the sun over a huge farm to generate power on Mars. So one might ask, why are we not doing that more here? We should be, right? So I think the one thing that we have no shortage of here on planet Earth is space and an atmosphere, which we're obviously polluting by not using things like solar panels a bit more. But generating your own power is a way that you can become self-sufficient here on Earth, as well as self-sufficient on Mars. The other one, which we don't have to deal with here on Earth, is radiation protection, because we have a very thick atmosphere and we have a magnetic field that actually protects us from the high energy particles that are coming from space. On Mars, this is actually a challenge because you are getting some radiation from the sun as well, but you're getting a lot of radiation from deep space, which happens to be really high energy and will basically cause cancer if you don't do something to protect yourself against it. So when you're living on the surface for an extended period of time, that has to be mitigated. The good news is that we now have a reading of what that radiation level is from the Curiosity rover, so now we can design a shielding technology solution to mitigate that radiation. So once you know the sort of like the amplitude and the frequency space of that energy, then you can actually design a shield to protect you from it. And the good news on Mars is that you can be, once again, self-sufficient by creating subterranean habitats or even structures out of Martian soil to make bricks to protect you from that. Water, this is another really important one. It is an abundant resource here, but we're also that's also a challenge as well as the climate changes, so we do need to address that. And on Mars, there's water frozen in the subsurface. You can imagine actually utilizing that to move your, to basically convert it into oxygen and hydrogen, which can be fuel, and then of course for eating and for washing and for all the other needs that people need water. Another aspect of sustainability on Mars is methane. You could actually create your own rocket fuel so that you can get back to Earth, because no one's going to live there, forever. They will still have the ability to go back and forth. And then another really important one is extremophiles, which are plants which have the ability to grow with very little oxygen, lots of CO2, and as a result, they produce oxygen from this photosynthetic process. And so, admittedly, that is a genetically engineered plant. I know that's not popular here in Europe, but if you're going to Mars, you probably are going to want to do something on that front just so you can get enough food volume to keep people going. So that kind of leads me to my last question, which is, would you want to live on Mars? So I think it's probably going to happen. The first people will probably go there in, let's say, 15 years. I think certainly in all of our lifetimes, we will go there. Will there be a colony in all of our lifetimes? Probably not. But would I say in the next 100 years or so, would things be setting up there? I think so, because I think there's enough of an interest now, especially from the business community side, to be able to support
those kinds of developments moving forward. And so even though these are all different transportation technologies, whether it's the Hyperloop, whether it's urban air taxis, whether it's launch vehicles or reentry vehicles, they all use the same principles of aerodynamics, of control, and of designing a set of requirements based off of what your customers need. So to wrap up, I have, I think, 5 or 10 minutes to take questions, so I'm happy to answer questions on anything from the space program side of things, the Hyperloop side of things, or urban air mobility side of things. And you can also ask me questions afterwards on my Twitter account, too. So thank you. And I don't know how we're doing the questions, but thanks.